Hello USHS students. I hope everyone is doing all right and you're finding these videos to be fairly simplistic and still getting the information across to you. What we're going to talk about today would be isotopes. We discussed what atoms were, those basic building blocks of all matter. We talked about what those atoms are made up of, the subatomic particles, those protons, neutrons, and electrons. Well, today what we'll do is we'll dive just a little bit deeper and we'll see how those individual elements, they can have twins or triplets of themselves. All right, I call them twins or triplets, but the scientific term that we're going to use would be isotopes. All right, so as I go through the notes, make sure that you pay attention to any of the red bold-faced words and you fill those into the correct spots in the guided notes. At the end of this, there will be a quiz right away. I did throw an extra little item on. It's going to be some fill-in answers. If you don't want to search the web for uses of these isotopes, I provided a video for you at the end of it that you can click. It'll go right to YouTube. It'll have a lot of different medical uses of isotopes. It's pretty interesting. Okay. As we go through this, try to keep that focus on what the key vocabulary terms are. I've got them down there at the bottom. We'll touch on those as we go. All right. So off we go. Okay. First, let's define what an isotope is. So an isotope, you're just looking at the exact same element, but there's differences in that element. Okay. For example, if you had, let's say a family that you know, and they're twins or triplets. Now, those twins or those triplets, they might look exactly the same. They might even act the same, okay? But if we were to put them on a bathroom scale, they may not be the exact same weight. All right, so we can think of isotopes as those twins or those triplets that look and act exactly the same, but they don't weigh the same thing. All right, now, when we're talking about those twins or triplets and they act the same way, they look the same way, well, what makes isotopes the same? It's the number of protons. See, an element is identified by the number of protons found inside of the nucleus of the atom. So if you have hydrogen, all right, hydrogen has one proton in its nucleus. All right. Now, hydrogen has a twin brother or sister, if you want to think of it that way, and it looks exactly the same. Now, what's the difference between these two hydrogen siblings is hydrogen 1, that would be this one right here, it has no neutrons in the nucleus of its atom. So its weight on a bathroom scale would simply be 1 atomic mass unit. All right, now if we look at that hydrogen's brother or sister isotope here, if we look at this one right here, what's the difference with it? Well, this one, it looks the same because it has one proton. It's going to act the same because both of them have the same number of electrons, 1. All right, but what's different is that this one has a neutron in the nucleus of its atom. So if it has one proton, that's 1 AMU. If it has one neutron, it has 1 AMU. So its total mass number is 2. Now, it just so happens that hydrogen has a third sibling. All right, now this one, the name for this one is called tritium. Tritium, it's an unstable isotope of hydrogen. Now, tritium is a triplet, is an isotope of hydrogen. What makes it the same as its two siblings would be that it has one proton in the nucleus of its atom. All right, now what's different with this one, this unstable isotope of hydrogen, it can't control itself when it goes to the refrigerator. It's just going to eat and eat and eat and eat and eat. And as a result of that, it's going to be a little more weighty. It's going to have not one neutron in its nucleus, it's going to have 2 neutrons in its nucleus. So that would give it a mass number of 3. So since this one would be an unstable one, I'm going to shade it a little different color. All right, so these 3 triplets of our hydrogen atom, we have protium, that's this one right here. You have deuterium, you have this one right here. And then as I said, this one right here is tritium. All right, so those variations, there's a lot of different variations of our elements on the periodic table, and just a little bit of our 81 that's listed as our naturally occurring. We'll find that there's 275 different isotopes of those particular stable materials. Okay, so we'll touch on that in just a minute. All right, so chemical properties. All right, with the exception of hydrogen, the chemical properties of all the isotopes are very similar, if not identical to one another. Now, what makes that particular characteristic, what makes those chemical properties the same for these different isotopes? It's the number of electrons that we have for each one. All right, now, if we're looking at sodium, for example, sodium has our 11 protons. So I'm going to put here, I'll do a Bohr model. We go plus 11, that's our nucleus. Now sodium, if it has 11 protons, we know that we're going to find 2 electrons on the innermost level. We go to the second energy level, and we have 11 electrons that we have to fill in here. On the second energy level, we're going to have 8 electrons. And then when we get to that valence shell, that outermost energy level, what we're going to find is it has 1 outer electron here. So if we had isotopes of sodium, what we're going to find is that sodium, every single sodium atom is going to react the exact same way. It's going to react very violently when it's put in contact with water. And why does it react so violently is because it does not want this electron right here. It wants to lose it rapidly. It needs to get rid of it, so that way it has an octet of electrons. It has that second energy level that contains 8. So this thing, all these sodium atoms, they're all going to react the exact same way. They're all going to be violently reacting with water, giving up that 1 electron. Usually we're forming those ionic bonds that are associated with our metals. Okay, so it's the electrons that determine the way an element is actually going to behave, how it's going to act, how it's going to react or bond with something else. Okay, so I gave you one example. Another common example, if we're looking at isotopes, would be chlorine. Chlorine, we're talking about the stuff that you'd put in your swimming pool to help keep it clean. We're talking chlorine that would be that you'd find in bleach that would help to brighten your whites. Okay. Now, this chlorine, I'm just going to give you 2 of the common examples of chlorine. All right. So first, we'll go ahead and put down chlorine. If we're looking at 2 isotopes of this. Now, the first thing I want to point out is that chlorine, regardless of what the actual isotope is, we're going to have the exact same atomic number of 17. So I'm going to put down here 17. Now this is one way that you want to write out what the actual isotope of your element would be. So we write down chlorine 17 because that's the atomic number. Now that means that this chlorine atom has 17 protons in the nucleus of its atom. All right, that's what tells us that we're looking at chlorine. What's different here is that we have chlorine 35. Okay, so I'll put 35 here. And then we have chlorine 37 right here. So we will find these 2 different isotopes of chlorine. Now, there are other ones, but these are the most common. All right, now, of these particular chlorine isotopes, what's going to be different with these? It's going to be the number of neutrons that you find inside the nucleus of our atom. Okay, so we're going to have for chlorine 35, all right, so another way you could write this out, you could go chlorine 35, you could go chlorine 37 here, you have 17 protons. We don't know right offhand the number of neutrons, but we do know that the mass of these two things added up have to be 35. So if we do the math of this, we've got 35 minus your 17, you've got, what's that going to be, 18, if I'm doing my math in my head right. Yep, that is 18. So all I did was I just subtracted the two values. We have to have a mass number, okay, or mass number for that particular isotope is 35. Now if you go over to chlorine 37 now, this guy right here, it also has 17 protons. And our number of neutrons, we're going to have a certain number of neutrons to equal that mass number of 37. Well, if we do the math of this is a little bit easier here. It's going to be 20 neutrons. All right, now that gives it its look. That gives it its look. What is this thing going to be? It's going to be chlorine, regardless of what the mass is going to be. All right, now what is going to give it its characteristics? That's the number of electrons. All right, so if this guy has 17 protons and we find it on the periodic table, it's going to be electrically neutral. That means that it's going to have 17 electrons also. So regardless of which isotope of chlorine that you're going to have 17 electrons if it's electrically neutral. Now, what you are going to find is that I said that you use this chlorine in your pool, you use this chlorine in your laundry in the form of bleach. But if we just had straight chlorine in a bucket, all right? If we just had straight chlorine in a bucket and you reached in there and if you could grab chlorine atoms, how often would we reach in the bucket and pull out a chlorine 35 atom? Well, what we've calculated is that it would occur, now I'm going to round this off, 75.78% of the time you are going to find by abundance chlorine 35 in nature. Now that means, now again, you have to understand I'm not putting in all the chlorine isotopes, we're just using the two most common ones. All right, that means that the rest of the time that you reach into the bucket, how often are you going to be pulling out a chlorine 37 atom? That means that based on abundance, you would be pulling out 24.22% by abundance chlorine 37. So when we're looking at these isotopes, it's not just a 50-50 ratio or you take the number of isotopes you have and you divide them by the quantity. No, you have to know how much is going to actually be occurring in nature. All right, so we do have to look at percentages. And when we look at those percentages, it's these values right here that's going to help us determine what the weighted average of our atomic weight is going to be recorded on the periodic table. Because what you should notice, as I keep saying these values, I keep saying that chlorine 35 and chlorine 37, but on the periodic table, it's recorded as 35.45. Where did that 0.45 come from? Well, if we're taking into account the percent abundance, how often we find chlorine 35, you can see right here that chlorine 35 occurs more often in nature than what chlorine 37 does. So when we do a weighted average of these two values, we record that weighted average on the periodic table. So since chlorine 35 occurs more often in nature, that means that the weighted average on the periodic table, that 35.45, our value for the weighted average is going to be closer to the one that's more common. Okay? All right, so some physical characteristics. The physical properties of isotopes vary to each other since their properties often depend on the masses. All right, now what we're kind of looking at here is I want you to think of these isotopes as if it were you carrying some boxes, okay? So here you are, you're trying to, my perfect pictures here. So you're carrying some boxes. Now, if you're just carrying one box, it's going to be pretty stable. It's not going to fall over at all. All right, but as you start to add more and more and more boxes onto this, what's going to happen? Well, what's going to happen is the whole stack is going to become a little unstable, and these guys might just fall off until it becomes stable. So the more mass you have, okay, the more mass you have might take and result in something that's not very stable. Okay, we're going to touch on that in a minute. So how do we separate all these isotopes up? Well, you can use what's called fractional distillation. We actually use that distillation process when we're separating up crude oil. You separate up crude oil into all the different byproducts. If you're looking at diffusion, you probably talked about diffusion from areas of higher concentration to lower concentration in biology. So we can use those same practices in separating up these different isotopes. All right. So what you should have noticed is that there's two ways that I showed you how we can write these isotope names. All right. So we always write down the element name first, and then we follow it up with the mass number. So I gave you the example chlorine, so I'd put down chlorine, and then we had chlorine 37. Or if you have carbon, one of the isotopes of carbon is carbon 12. Well, you don't always have to write out the full carbon. What you can do is you can just write down the symbol. So I can put down right here for chlorine, I could put chlorine 35. But then you're also going to notice something, that in the examples that I gave you for hydrogen, the three isotopes of hydrogen, I started out with the symbol, and then I put two numbers on the left-hand side. It is always on the left-hand side. You always put the charge of it, the number of protons, down at the bottom. So we have chlorine, its atomic number was 17. In this particular isotope, it has a mass of 35. So there's just different ways that we can write these out, okay? So make sure you get the C12, the carbon 13, C13, and superscript in the right spots for those guided notes, all right? Moving on. In most cases, the isotopes of elements have the same name and are recognized with different mass numbers on the suffix. All right, those different mass numbers come from us looking at adding up the number of protons and neutrons for each of the individual isotopes. So let's say this one right here, if we look at oxygen, for this we'd have our symbol oxygen, atomic number, we have oxygen 8, all right, and what's going to be the difference? When we're writing out the names of these different isotopes, we'd put the mass number up top. We'd have 16, 17, and 18. And what's the similarity here? They all have 8 protons. They all have 8 electrons. But the masses are different. This one here, that has 8 neutrons. This has 9 neutrons. This has 10 neutrons. So the masses are different. Okay? Now, we had one exception to this is hydrogen, and if we're looking at these, the one that I had talked about with this, I had mentioned that that tritium is going to be that unstable isotope of it, but we're looking at in terms of our actual isotopes themselves, you're going to see that every one of these has the exact same number of protons, the exact same number of electrons, but their number of neutrons are going to differ. Okay, so we just have hydrogen. We'd say hydrogen, this is our deuterium, and then this is our tritium right here. So it gives you a little bit of a graphical picture of it. All right, stable isotopes. This is going back to my analogy of you carrying around a box. All right, you're carrying around a box, and then you put another box on top, and then another box on top. Well, those are your protons and neutrons that you have inside of your nucleus of an atom, right? Just because you think you can carry more groceries in from the car doesn't necessarily mean it's always going to be stable. You may have to make 2 trips for this, all right? So when we are looking at atoms and you have a certain number of protons and neutrons in there, we've got to have the right blend of them in order to produce a stable atom, right? If you have too many neutrons, it might increase the instability of that atom. If you decrease the number of neutrons, again, you might decrease the stability of that atom. All right, so whenever you have something that is unstable, we can have it undergo radioactive decay. It wants to become stable. So you're trying to carry in a whole bunch of boxes, a whole bunch of bags from the car, and all of a sudden a few of them fall off. Well, you can think of that example of the atoms falling off, or the boxes falling off, as radioactive decay. So in the example I give you here, we have bismuth 209. It's a stable radioactive isotope, but it does undergo alpha decay. It gives off those alpha particles. And if you remember us talking about Ernest Rutherford, we're talking about those helium nuclei that are being shot out of that material because it's unstable. The boxes are falling off of you when they're stacked up. All right, we call these radioactive isotopes radioisotopes. All right, now those radioisotopes, they're going to be kicking out subatomic particles. If we're looking at that example of Ernest Rutherford's, we were kicking out those helium nuclei. We were kicking out those protons. If we're looking at beta minus decay, we're going to be ejecting electrons at high rates of speed. There's a little more to that, and we'll get to it. But whenever we have this radioactive decay taking place, the identity of that atom is going to change, because if we have the subatomic particles changing inside of an atom, then you're going to have a different atom that's going to take a presence, or it's going to show up. Now, what do we call that initial isotope? Well, we call that the parent isotope. And then as that parent isotope breaks down, as it begins to decay, we call the products of that the daughter isotope. Okay. One example of this would be when uranium-238 decays into thorium. All right. When this decays into thorium, we're going to see that we have daughter isotopes that are going to occur. So no longer are we looking at uranium-238. We have our mass and our atomic number that's going to be changing as a result of that. Now, those subatomic particles that are being ejected out, that doesn't mean that they're destroyed. It's changing form. Okay? So where do these isotopes come from? Other than radioactive decay, we might say that it's been hypothesized that the lighter isotopes, they actually came together sometime during the Big Bang, while heavier ones were made in the cores of stars. So we might have had some that are actually coming together based on gravitational forces. They're combining together. We could have cosmic rays that start to energize particles in the upper atmosphere, and that leads into forming of unstable isotopes. Now, we're going to talk about this one here a little more in depth in just a moment. All right, so what are some uses of these isotopes? One of the uses that we can have when we're trying to use isotopes would be in the form of carbon dating. If you'd like to find out how old a fossil is, it's possible to figure that information out by looking at the half-lives of different isotopes. And the isotope that's used for this carbon dating is carbon-14. All right, we are going to talk a little bit more about how carbon-14 takes place, okay, but we'll get through this slide first. All right, carbon-14, its half-life is 5,730 years. That means that over the course of that time frame, half of that material would decay. So, if we're looking at where carbon-14 originates from, it's in the atmosphere. Okay? It combines with oxygen. That radioactive carbon dioxide is then taken into plants. Animals eat the plants, right? And as they're eating those plants, as the carbon dioxide is going into the plants themselves, for about every trillion stable carbon-12 isotopes that they're taking in, they're also taking in carbon-14 atoms, those unstable ones. All right, so while those animals are living, they continue to take in carbon-12 and carbon-14. Now that remains stable. It remains stable throughout that organism's life because as that carbon-14 is breaking down, it's also taking in more carbon-14. You're eating more animals that have consumed the plants that have taken in that radioactive isotope. So there's always a balance. Now, the only time we lose that balance is if you stop eating. If the organism dies, it's not taking in any more carbon-14. Now, if you stop taking in carbon-14, carbon-14 continues to decay. So what we can do is we can use mass spectropy. Oh my gosh, I probably, this is one of those words, like some people have troubles with aluminum. This is mine, okay? So what we can do is we can analyze the sample. We can figure out how much carbon-14 is remaining inside of that sample. And then from that remaining amount, we can see how much carbon-14 remains compared to what it should have had as a standard, okay? And we can date that organism's life. Now, let's take a look at, I said that I wanted to do this. I wanted to get into a little bit more about where this carbon-14 comes from. All right, now first, if you're looking at carbon-14, you have in the atmosphere, everybody should have an idea of what the most common gas in the atmosphere is. You have nitrogen. All right, so nitrogen, we have 14 and 7. All right, so that means that the most common nitrogen atom, we have 7 protons and its mass is 14, so it has 7 neutrons also. Now, in the atmosphere, it's constantly being bombarded. All right, now one of the things that hits that nitrogen-14 molecule is going to be a high energized neutron. All right, now if a high energized neutron, so we'll say this is my neutron right here, if that high energy neutron strikes the nucleus of an atom, we have 7 protons, we have 7 neutrons here. Okay, if that neutron strikes the nitrogen atom, what's going to happen is it's going to hit this nitrogen atom, okay, and it is going to eject out of it. So this is beforehand. It's going to eject out of that a proton. All right, so a proton, it gets shot out. It's like a game of pool. You hit the pool balls, something's going to move, right? So now if it shot out one of those protons, now it only has 6. All right, what happens to its mass? Well, now it has 8 neutrons, okay, because it replaced it, it knocked it out. Okay, so our mass remains the same, but what is this atom now? This atom now is no longer nitrogen. This atom is carbon. All right, now carbon-14, it's that one that we use for radioactive, that radioactive decay of carbon-14 in our carbon dating. So that carbon-14, this guy right here, this is an unstable isotope of carbon. If it's in the atmosphere, it's going to combine with what? Oxygen. And it's going to form our unstable, and this is going to get kind of ugly here, an unstable carbon atom is going to combine with oxygen. Now that carbon dioxide molecule, where does that go? That goes into plants. Okay, so it goes into plants. Plants are eaten by animals. You consume them. And the thing is the amount of that radioactive carbon, it stays constant throughout, the time in the atmosphere, the time in the plant, the time in the animals. The amount that's being produced and the amount that's breaking down is consistent. All right, so if you stop eating, if a plant dies, if an organism dies, all of a sudden we don't have this balance anymore. Animals, they stop consuming this radioactive carbon atom. So what's going to happen here is you're going to notice that the decay of this is my carbon atom, okay? It's going to undergo what's called a beta minus decay. Now in a beta minus decay, what's going to happen here is that beta minus decay is going to cause one of these neutrons, okay? So I'm going to put this down here, beta minus decay. It's going to cause one of these neutrons to actually change. And this can happen, this does happen. That neutron is actually going to change itself into a proton. All right, now if we're looking at that carbon atom and it's undergoing this beta minus decay, what it's going to do is it's going to change one of those neutrons into a proton. All right, now if it does that, the mass is still the same, right? We didn't change the mass here, but if it's 7, what element is that? Nitrogen. Okay. Now what else is happening here for this beta minus decay? We can't just have that and that's it. What you're going to get also is what's called a W boson. Okay. And that W boson, we're going to form an electron. It's going to be a high-speed beta particle that's going to be shot out of this beta minus decay. So you get that electron, that high-energy electron that's also going to be produced from this. Right now, maybe next year, if you have some more time, Mr. Arnold will talk more about radioactive decay with you. But I hope this is at least like a snapshot of what it is. Okay, so we're at the point where we can look at some uses. There's all kinds of uses. We mentioned one, you have radiometric dating, right? If you're looking at other uses, maybe you're looking at blood flow. If they put trace elements into your body, what they can do is they can follow the movement of those radioactive particles inside of your body, and then they can get a map of where all of the blood might be moving. If you're looking at all kinds of other uses, I do have a video that I'll share at the end of this, okay? But if we're looking at one last use, okay? If we're trying to make uranium that could be used inside of nuclear reactors, you want to enrich that. All right. So if you want to enrich our uranium atoms to make them usable, then that's another use of isotopes. All right. So I know that was kind of quick, a little bit longer than the other ones, but definitely not as much as I would have liked to have gone over. I'll leave a link for the video to help you in terms of identifying other uses and the fill-in answers on the quiz. If you have questions, please let me know. Until the next video, just make sure that you get all your stuff turned in, and we'll move on to next week. All right, take care.